Pluto is a far-off and stealthy, more unobtrusive planet that was once a part of our nearby planetary system. However, recent groundbreaking declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They have suggested that this chilly world is on a potential crash course with Neptune. But how could this really happen, and what might be the consequences of such a titanic event? Are we witnessing an intriguing cosmic phenomenon, or is there more to this impending celestial collision? Join us as we examine the possible outcomes of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of fascination and study in the astronomical community. According to recent estimates by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a potential catastrophic collision between these two planets, which could pose a significant risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it has not yet completed one full revolution. However, the intrigue does not stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is far more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For approximately 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying conventional expectations of planetary positioning. This raises the fundamental question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unusual path. Unlike other planets, whose orbits remain relatively close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and elongated shape. The mystery deepened when it was confirmed that Pluto's orbit does, in fact, cross Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space involves understanding how three objects, such as Pluto, Neptune, and the Sun, move and influence each other through gravitational forces. It's like predicting the motion of celestial bodies based on their starting positions and mutual gravitational pulls. In Pluto's case, this problem explains how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex yet stable manner. Several key orbital mechanics concepts play a crucial role in maintaining this stability. 1. Resonance and orbital synchronization. Pluto and Neptune exist in a 3:2 orbital resonance. This means that for every 3 orbits Neptune completes, Pluto completes exactly 2. This gravitational relationship prevents close encounters. 2. Orbital precession. This refers to the gradual shift in Pluto's orbit over time. When Pluto is closest to Neptune, it is positioned far above Neptune's orbital plane, adding another layer of protection. 3. VZK oscillation. Named after astronomers Vashkov, Zeldovich, and Kai, this describes how 3 celestial bodies, Pluto, Neptune, and the Sun, influence each other gravitationally, stabilizing Pluto's orbit despite its seemingly chaotic nature. Even though Pluto's orbit appears erratic, these factors work together to maintain its long-term stability. The VZK oscillation illustrates that, despite the apparent chaos in space, certain patterns and laws keep celestial objects in stable paths. Mathematical simulations in the late 1980s revealed that Pluto's orbit, while stable over long timescales, is still highly sensitive to minor perturbations. Small deviations in initial conditions could lead to significant differences over thousands of years. However, later automated studies have shown that the influence of giant planets like Neptune, Jupiter, and Saturn plays a crucial role in maintaining Pluto's stable orbit around the Sun. Neptune, in particular, has a unique relationship with Pluto. Their 3:2 resonance helps maintain Pluto's stability. However, Neptune is not acting alone. Jupiter's massive gravity also plays a major role in stabilizing Pluto's orbit, with Saturn contributing as well. These studies demonstrate that Jupiter's immense gravity is strong enough to ensure Pluto remains on a predictable path for millennia. In a way, Neptune, Jupiter, and Saturn are working together to keep Pluto moving safely through space without colliding with other celestial bodies. Without these stabilizing factors, our solar system would be a much more chaotic place. Bodies like Pluto could crash into others or be ejected from their orbits, potentially triggering chain reactions that could disrupt the entire planetary system. For Pluto, especially with discussions about a possible future collision with Neptune, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of the solar system. Pluto's case demonstrates that even seemingly unstable orbits can reach a state of equilibrium through the intricate interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and research to better understand our place in the universe. Exploring the depths of space often leads us to confront the unpredictability of celestial bodies, and Pluto's orbit is a perfect example of this phenomenon. The concept of orbital chaos, which describes how the trajectory of a celestial body can be highly sensitive to initial conditions, is vividly illustrated in Pluto's case. Even minor changes in Pluto's position or velocity could drastically alter its long-term orbit. Using advanced automated simulations has greatly helped researchers understand how Pluto moves through space. These simulations use complex mathematical models to predict how Pluto and other celestial bodies interact gravitationally. By adjusting small parameters in these simulations, scientists can see how even minute changes can have significant impacts on Pluto's trajectory. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. While it possesses stabilizing mechanisms such as resonance and precession, its path can still be irregular and unpredictable. Even a slight difference in Pluto's starting position or speed could result in an entirely different orbital outcome. Following a couple of years, yet even with this disorder, Pluto's orbit remains stable over truly extended lengths of time, like billions of years. This genuinely implies that Pluto's journey around the Sun has a sort of order to it, despite the fact that it initially appears to be tumultuous. Predicting celestial events, especially when they involve chaotic orbits like Pluto's, is a gigantic challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical models provide valuable tools for understanding and forecasting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise estimates a daunting task. Furthermore, the turbulent nature of planetary orbits like Pluto's reminds us of the ever-changing and dynamic nature of the universe. While we've made enormous strides in understanding space, Pluto's case reminds us how much our knowledge of the universe remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly influence the stability and direction of other bodies within the system. So, why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune, despite the complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a major figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public interest in the often overlooked realms of space. Tyson's position on Pluto's reclassification is based on the ever-expanding knowledge of our solar system. He views the renaming not as a demotion but as an important adjustment to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a testament to how much there is still to discover in space. The pursuit of these questions keeps space exploration so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the future of Pluto's orbit suggest that we may still have many secrets left to uncover. Will Pluto collide with Neptune, or is this just another moment of confusion in the ever-changing universe? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we truly understand about our own solar system. We continue studying these celestial phenomena, hoping to uncover more of the mysteries that lie beyond. The possibility of a Pluto-Neptune impact raises yet another question about the enigmatic and captivating universe in which we exist. The potential for such a collision brings up fascinating issues regarding the dynamics of the solar system, as it challenges conventional understandings of planetary stability. That two celestial bodies with such vastly different characteristics could collide is both unsettling and intriguing, especially considering the current relative stability of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be immense for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the composition and properties of both planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere primarily composed of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is composed mainly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would dramatically affect their structure and behavior, possibly creating an event visible across vast distances. What makes this hypothetical impact particularly fascinating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another key component. Jupiter's immense mass, strong gravitational field, and gravitational pull provide a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's territory. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it less likely that a catastrophic event will occur between Pluto and Neptune. Despite the apparent risks, ongoing research has shown that the relationship between Pluto and Neptune is not as simple as a straightforward collision course. The gravitational resonance between the two planets, where, for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a sort of cosmic lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while crossing in the vast expanse of space, have never resulted in a collision. The orbital mechanics of these bodies are aligned in such a way that the potential for conflict is minimized. To further understand the complexities of Pluto and Neptune's relationship, it is crucial to consider how their orbital behavior shifts over long periods. Although Pluto's orbit crosses Neptune's, the two bodies never actually collide due to their gravitational resonance, which ensures they remain safely locked in a stable pattern. This remarkable cosmic dance results from the two planets' orbital periods being in a 3:2 resonance. Pluto completes 2 orbits around the Sun for every 3 that Neptune completes. This synchronization ensures that, even though their paths may cross in space, Pluto and Neptune are always far enough apart at any given point in their orbits to prevent a collision. This resonance is a beautiful example of how the delicate balance of forces within the solar system works to maintain stability. Without this type of orbital harmony, Pluto would be at risk of drifting into a more chaotic path, potentially interacting with Neptune in a way that could disrupt the balance of the outer solar system. The gravitational interactions between planets, especially those as massive as Neptune, Jupiter, and Saturn, also act as protective forces, keeping Pluto in a relatively safe orbit despite its unusual characteristics. Beyond the gravitational forces at play, The overall structure of the solar system also plays a role in minimizing the likelihood of catastrophic events. The outer planets, with their immense gravitational fields, act as sentinels, constantly shaping and reshaping the orbits of bodies like Pluto. This constant interaction prevents the solar system from descending into chaos, with planets and smaller objects following predictable, though sometimes unexpected, paths. Despite these stabilizing forces, an element of unpredictability remains in the long-term evolution of the solar system. As we continue studying the behavior of bodies like Pluto, we are reminded of how much we still have to learn about the dynamic, ever-changing nature of our universe. While a collision between Pluto and Neptune remains highly unlikely due to their orbital resonance and the gravitational influences of other planets, it still serves as a reminder of the intricate and fascinating forces at play in our solar system. The possibility of such an event challenges our understanding and keeps us eager to explore the mysteries of space.